Swayam Prabha. Digital India. Educated India.
But now, the length L, as we had discussed earlier, is the distance between A and B, and this distance is as measured by the ground observers. And this distance is length contracted compared to the actual length between A and B on the train, or the proper length between A and B. So the length L is related to the length L prime, but it's smaller by a factor of square root of 1 minus v square over c square. That is its length contracted relative to L prime. So if you plug this in over here, we have L is L prime into the square root of 1 minus v square by c square. And therefore, the parent phase delay between the clocks A and B, between clocks A and B, would just be V over C square times L prime. And this expression is in exact agreement with what we expected from the Lorentz transformation of the offset between the clocks, or the phase delay, being V times L prime over C square. All right, so now we have an intuitive perspective of, given the constancy of the speed of light to all observers, we now understand why the clocks in the train would not appear to be synchronous, and in fact would just have a phase delay. The next thing that we would like to do is to expand our dictionary. So now that we know in special relativity how to translate observations between one observer in a frame S and another observer in a frame S prime, who is moving at a speed v relative to the first observer, we know how to make a translation between the time, position, coordinates to the time and position coordinates as measured by the second observer, and these are just related by a Lorentz transformation. However, in Galilean relativity, we saw that there are more things that we want to derive a dictionary for. We need more words in which we can translate between the frame S and the frame S prime. For example, we might be interested in knowing if we have an object as seen in frame S prime, which is moving with a speed u prime, say, what does that speed, or what does that velocity look like in the frame S? So what is the velocity u prime as measured in the frame S? So what is the dictionary equivalent of u prime? And similarly, we'd like to know this for accelerations as well. If we have an acceleration in the frame S prime, what is the corresponding acceleration in the frame S? In Galilean relativity, the dictionary was fairly simple. Time was absolute, space was absolute, but the x-coordinate was the only thing that changed, assuming that relative motion, let's say, was along the x direction. X prime was x minus vt, y prime was y, z prime is z, but we had no phenomena of things like length contraction or time dilation. And if we expanded this dictionary to include velocities, so an object moving with a speed u prime in the frame S prime, as seen by observer S, would also pick up an additional speed, which would be due to the velocity of the train. So that is, the speed u would be equal to the speed u prime plus the relative speed of the frame S relative to the frame relative speed of the frame S prime relative to the frame S. And finally, we saw that the accelerations would just be the same, okay, in both reference frames. So we have a dictionary for coordinates and we have a dictionary for which includes more words, such as how velocity is transformed and how acceleration is transformed. Now, given that our dictionary for time and space has changed radically, we might expect that there is going to be a change in the dictionary equivalents for the speeds or the velocities. So as a vector equation, this is more precisely written in this way. And what we'd like to know is how this equation changes when we go to special relativity. So let's derive the transformations for velocity in special relativity. So let's suppose we have a frame S prime, and this is the x and y directions in the frame S prime. And according to an observer, or a frame S, this frame S prime is moving along the x direction with a velocity v. Okay, and in the frame S prime, for example, on a train, some observer throws a ball relative to themselves with a speed u. And we can break u into two components. We can decompose this vector u into a component which we call u parallel, which is parallel to the direction of relative motion, and a component u perpendicular, which is perpendicular to the direction of relative motion. And as we've seen, since lengths and do different things when we are talking about lengths parallel to the direction of motion and lengths perpendicular to the direction of motion, it's better if we make this separation already at this stage and consider the dictionary separately for the parallel component of the velocity and the perpendicular component of the velocity. So u parallel, or let me write this as u prime rather, u prime parallel, will just be equal to the distance traveled by this particle or this ball as measured in the frame S prime divided by the time it takes as measured in the frame S prime to travel that distance. Okay, this is what u parallel prime would be, and u perpendicular prime would be, let's say, the distance it travels in the perpendicular direction divided by the time it takes to travel in the perpendicular direction. And now we can apply our dictionary to find what the corresponding distance delta x would be, the corresponding time interval delta t would be, and the corresponding distance interval in the perpendicular direction delta y would be. Okay, and we can, if we know delta t, delta x, and delta y, that is, we know the distance it travels in the x direction and the time it takes as seen by the ground observers to travel that distance, then we can get the parallel component of its velocity, okay, as measured in the frame S. So this is in S prime. In S, we can get u parallel, which would be delta x over delta t, and we can get u perpendicular, which would be delta y over delta t. So in other words, we're using our dictionary for delta t prime, delta x prime, delta y prime, mapping it to delta t, delta x, delta y, and then using it to derive the dictionary. So these are derived words in our dictionary for u parallel and u perpendicular. So let's first write down the dictionary for u parallel. And for this, we'll need to know how to translate delta t and delta x. So delta t would just be equal to 1 over the square root of 1 minus v square by c square times t prime plus vx prime over c square. Remember that this is an inverse Lorentz transformation because according to the frame S prime, the frame S is moving relative to the frame S prime at a speed minus v. And similarly, delta x would be 1 over the square root of 1 minus v square over c square times x prime plus v t prime. So we can plug in, since we're talking about a time interval, we should use delta t prime here. And we should use delta x prime here, and similarly delta x prime here, and delta t prime over here. And so now we can derive what u parallel is. So u parallel, which is by definition delta x over delta t, this is by definition. And now using our dictionary, we can say that this will be delta x prime plus v delta t prime divided by delta t prime plus v delta x prime over c squared. And now we can divide both the numerator and denominator by delta t prime, and this would give us delta x prime over delta t prime plus v divided by 1 plus v delta x prime over delta t prime over c squared. And finally, we can use the fact that by definition u parallel prime was delta x prime by delta t prime. So we can finally write our dictionary. So this is a derived dictionary word, is u parallel prime plus v divided by 1 plus u parallel prime v over c squared. Okay, so we've expanded our dictionary now because we can now write u parallel in times of u parallel prime and the relative speed v. And now we can do something similar for u perpendicular. For u perpendicular, we need to know the dictionary for delta y. So delta y would just be delta y prime. And so the dictionary word for u perpendicular, which is by definition delta y over delta t, we can use our dictionary now to tell us that this will be delta y prime over, using our expression for delta t, we get delta t prime plus delta x prime times v over c squared. And then don't forget about this factor of gamma. So there's a 1 over square root of 1 minus v squared by c squared. So finally, what we get is u parallel is equal to delta y prime over 1. So again, dividing by delta t prime in both the numerator and the denominator, times the square root of 1 minus v squared by c squared. And so what this gives us finally is u perpendicular is, and this is by definition u perpendicular prime, divided by 1 plus this quantity here is u parallel prime times v over c squared. And the whole thing is multiplied by 1 minus v squared by c squared. So we derived a second dictionary word, so it's useful to compare these new dictionary words with what we had in Galilean relativity. In Galilean relativity, u parallel was just u parallel prime plus v. This was in Galilean relativity. In special relativity, we see this additional factor in the denominator. Okay, and in Galilean relativity, the perpendicular component of the velocity doesn't change. So u perpendicular is equal to u perpendicular prime in Galilean relativity. But here we see that there's a more complicated change where the perpendicular component of velocity as seen in frame S depends not just on the perpendicular component as measured in frame S prime, but also on the parallel component of the speed of the ball as measured in frame S prime. And it also depends on these factors of v. Okay. Now, in a particular limit, suppose the object has only a perpendicular velocity in the frame S prime, then u perpendicular prime is non-zero, but u parallel prime is 0. And in that case, u parallel or u perpendicular is u perpendicular prime times the square root of 1 minus v square over c square. Now, in this case, it's easy to understand why the dictionary is different from the dictionary of Galilean relativity. In the perpendicular direction, there is no length contraction, so the distance traveled by the ball in the vertical direction would be exactly the same as seen by S prime and another frame S which is moving horizontally, let's say in the x direction. And however, there is a time dilation effect. So the time that this ball is traveling in the frame S prime appears to be smaller than the time that it travels in the frame S. So therefore, the speed in the frame S prime would appear to be higher, or it would appear to have a larger speed. And the speed in the frame S would appear to be lower. And the difference between the two is just the time dilation factor. Another interesting thing that we can see is if we go back, for example, to looking at the parallel component of velocity. Supposing we have an object which is thrown with the speed of light. Okay, so let's take light itself. So in the frame S prime, we have a light beam which is shined at a speed u parallel prime, which is equal to c. And this frame S prime is moving with respect to S at a speed v in the x direction. So now what we want to know is what is u parallel. So using our dictionary above, u parallel is u parallel prime plus v divided by 1 plus u parallel prime v over c squared. So what we would get is c plus v over 1 plus cv over c squared. And so what we would get would just be c. That is, the light beam which is traveling with a speed c as seen in the frame S prime would also be traveling with a speed c as seen in the frame S. This is good. We need this because this should follow from our postulates of special relativity. This is built into the postulates of special relativity. And it's good to see that it emerges also from our velocity transformation law. Now, as a homework exercise, you can also try this out for the case where u parallel prime is non-zero and u perpendicular prime is non-zero, but the total speed of the light beam is c. You can check that the square root of u parallel square plus u perpendicular square will also be c. And finally, I'll leave you with one more homework exercise, which is to show how the accelerations transform. And to do this, let's consider a frame S prime. And let's consider an object accelerating to the right with an acceleration ax prime. And this frame S is moving with respect to another frame, this frame S prime is moving with respect to a frame S at a speed v, then you can show that the acceleration of the same object as measured in frame S would be ax prime times 1 minus u, sorry, 1 plus u parallel v over c square cubed divided by 1 minus v square over c square to the 3/2. Okay, so the dictionary for accelerations involves not just the acceleration in the x direction, but also the parallel component of speed, that is the speed u parallel. Now, the dictionary for, you can also derive a dictionary for the accelerations in the perpendicular directions, which is a little more complicated. And one more important thing that I'd like to state here is that when you derive these transformations, you need to use the fact that ax prime is, by definition, the time derivative of ux prime, that is the speed as measured in the frame s prime, divided by, or differentiated with respect to the time interval in the frame s prime. So if you use this definition and the definition of ax, similarly as dux by dt by definition, you can derive this dictionary word. So let's summarize all the things that we've learned today. So the first thing is we saw how the new predictions of special relativity that is, things like the phase offset in clocks and time dilation, length contraction, arise as consequences of the postulates. They're just direct consequences of the postulates of special relativity. And the key postulate is the constancy of the speed of light as measured by all inertial observers. And then we expanded our dictionary to include some additional words like velocities and accelerations. And we saw that these transformations for velocities and accelerations are different from the transformations of Galilean relativity. So one particularly strange thing we saw is that perpendicular components of velocities do not stay the same, okay, and as measured in one inertial frame and another inertial frame. And another interesting thing that we saw is that the speed of light c is the same no matter which observer you talk about. That is, when I make the dictionary translation, and if the speed of the object that I'm talking about is light, then that speed will stay the same. So one word in our dictionary is known. When v is equal to c, the translation for that is v prime is equal to c. Where v is just the magnitude of the speed, okay, it's not guaranteed that the direction will be the same, and this is something that we'll see in the next class when we talk about light. And we also saw a dictionary for acceleration. So we've been able to expand our dictionary by deriving some words, that is the transformation law for velocities and accelerations, from the words that we already knew, which is the translations for coordinates. In the next class, we will expand this dictionary further and see how things like frequency transform, and we'll derive something called the relativistic Doppler shift.